Okay, let's go for global change, which is unit 9.3 and 9.4. We're going to be able to identify the greenhouse gases. We're going to look at sources and strength of those greenhouse gases and the threats from greenhouse gases to the environment and to health. Whew, a lot. Okay, so what is the greenhouse effect? It is when the sun's energy or warmth is trapped in our atmosphere. And it's called a greenhouse effect because that's literally what a greenhouse does. Energy from the sun comes into the greenhouse and it doesn't escape. It bounces off these clear ceilings and it keeps these plants inside the greenhouse humid and warm so they can sprout up and have a nice insulated heated environment. And that's also what happens on our planet. We need some greenhouse gases. Without greenhouse gases, no life would be on Earth. Convection wouldn't happen, air wouldn't flow, water wouldn't be in a current, and the mixing of the uneven heatedness of the Earth wouldn't happen, and we literally wouldn't have the water cycle or life. So we need some. We need the atmosphere to insulate the heat and let some of it out. And we call that the energy budget of the Earth. We'll talk about that in a minute. So the natural greenhouse effect, how it's supposed to work, radiation enters in through our atmosphere. It is light. The form of this energy is light. And then the light is absorbed by the surfaces on the planet and it re-radiates as heat or infrared radiation, which is what heat is, like a heat lamp, and that escapes back out into space. That's the basic idea. When humans are involved, we have extra gases in here, and so the heat from infrared that's trying to escape sometimes bounces off of the molecules in our atmosphere that are greenhouse gases, and it sends the heat back to the Earth, like the greenhouse that we talked about. Okay, so I'm gonna pause because there's like this airplane coming by. Hold on a second. Okay, sorry about that. Okay, so this Earth energy budget, this is a basic thing from Earth science, which I'm not sure you people have had because they kind of took it away in grade school. I don't know what's happening, but here we go. So the sun sends us an amount of energy. So whatever reaches the Earth, that's 100% of the energy reaching us from the sun. Some of that energy gets absorbed by clouds, some of that energy gets reflected by clouds. The gases in the atmosphere absorb some, and the gases in the atmosphere reflect some of that energy. And same with the surface of the Earth. Some of the energy is absorbed by the Earth's surface, and some gets reflected back. So this is the light coming in. Now remember, light is at a certain wavelength, the, the energy we can see with our eyes. Now, by the end of the day, the Earth has kind of absorbed a lot of this energy like a sponge, and then it emits or sends this energy back into the atmosphere and hopefully back out to space in the form of heat or infrared radiation. And so as this is coming out, some of it's put out by the clouds, some of it bounces off the clouds and gets reabsorbed to the Earth's surface. And so all this stuff happens. The big thing to know for apes is right here. So of all of this energy coming to our planet, about half of it, 50%, is absorbed by some surface on the Earth, water or land, plant, whatever. About 20% of it is absorbed by the atmosphere, whether that's clouds or gases in the atmosphere. And about 30% gets reflected back into space. So those are things to keep in mind. Wait for it. Okay, so the problem is we get too many greenhouse gases and then we get this imbalance of the greenhouse gases, and that's what starts to cause global warming. I just cannot win today. Okay, and this global warming is what leads to this climate change or climate disruption. So this picture is kind of cool looking, but I want to explain it with a simulation real quick, and I'll come back to this in one moment. Let's look at a simulation. All right, so here we have the global temperatures. We can put in some clouds if we want to, and we're going to add some greenhouse gases. So notice these greenhouse gases, carbon dioxide, methane, whatever it is, they're in the atmosphere. And watch what happens as we run this. And we've got the brightness of the sun set to 1, and then we have the albedo. Do you remember what albedo is? How reflective a surface is of the energy. So here we go. And we're going to run this. I'm running it fast. And you can see we reach a higher temperature, and then we kind of level out. Okay, I'm going to pause it. Now, what if I have a really low albedo? So a darker surface and more of the energy is going to get absorbed. Let's see what happens. Oh, we start to increase our temperature. It's starting to go up. So having dark surfaces causes an increase in temperature. I hope you can see that. Okay, what if we have more greenhouse gases? What if we just go crazy and we have like a bunch of greenhouse gases in here? That also seems to start to cause an increase in the temperature. It's going way up. But we could increase our albedo. Oh, look, it's starting to drop the temperature. So I want you to see there's a big relationship between albedo, the reflectiveness of surfaces, how much energy gets absorbed, and how many greenhouse gases are actually in the atmosphere. So that's important. Okay, so looking back at our picture here, we've got carbon dioxide coming down, and you can see this is reflecting out in infrared, and here's a water molecule, and instead of escaping back into space, it's bouncing off and re-radiating back down to Earth. Same with the methane. So these molecules, carbon dioxide, water vapor, methane, all kind of bounce the escaping heat back to Earth instead of allowing it to escape out into space, like that 30% we were talking about with our energy budget. So when we add greenhouse gases, we alter the energy budget. And so instead of this 30% getting reflected back to space, that may lessen the number. We may have more getting sent back to the Earth's surface, which will warm the planet. So here's a feedback loop flashback. Remember what a feedback loop does? Okay, so here's some things that happen. Warm temperatures cause evaporation, and so more water goes into the air. If there's more water vapor molecules in there, it's going to trap more heat. And that's just going to keep happening. So if there's more heat, there's more evaporation. There's more heat, there's more evaporation. And the more water molecules up here, the more that this greenhouse gas thing is going to be heightened. Now, a negative feedback thing is more water vapor can cause more clouds. Clouds trap heat, and they will reflect it back out, reflect it back down to the surface of the Earth. But also it will block sunlight from coming to the Earth and bounce that back out into space, and that could be a negative feedback loop. So this gets a little confusing because you could argue both sides of this for water vapor, not the other ones. So that's interesting to look at. Okay, so part of your thing is to know the greenhouse gases. So here we go. This one is not mentioned a lot, although it's the worst one. Sulfur hexafluoride, SF6. It stays in the atmosphere for about 3,000 years. What? Carbon dioxide, the one we always hear about, stays in the atmosphere for roughly 100 years, but we have the carbon cycle happening, so it's kind of hard to nail it down because it's always cycling through. Methane will stay in the atmosphere for about 10 years. Nitrous oxide will stay in there for around 100 years. The CFCs that we talked about in the previous lecture are up there for about 150 years. Water vapor, due to the water cycle, it's only up there for about 9 days before it cycles out. And ozone, also from our earlier um, lecture, 9.1 and 9.2, it's only up there for about 3 hours. Interesting. But these all have an effect on warming the planet and trapping those molecules like we saw. Okay, so carbon dioxide, we usually base it off of a value of 1, and then we compare all the other ones to it. So you can see some of these are way more greenhouse gas inducing than others. Human caused ones are in this little pie chart here. So you can see like these are not the natural causes of things, and the worst ones are the man-made anthropogenic ones. Okay, so where do all these greenhouse gases come from? So the one we're always worried about is carbon dioxide. Even though it's not a severe one and it stays there for 100 years and it only has a value of like global warming potential of 1, there's a lot of it, and we humans make a lot of it. So burning or combusting fossil fuels and coal and the crude oil, which are also fossil fuels, transportation. This is all carbon dioxide inducing gases, and it's adding to the greenhouse gases in the atmosphere. Methane from agriculture, using natural gas, landfills, and decomposition of different things is also contributing, and we'll find out in a second. Methane is a more heat absorbing greenhouse gas molecule than carbon dioxide. So even though there's not as much, it makes it worse because it's a heightened one. Nitrous oxide, so that comes from the cars, the NOx, the SOx, that makes that ground level ozone. Manufacturing processes, a lot of fertilizers and agricultural soil management has a lot of nitrous oxide in it. Then we have these perfluorocarbons from producing aluminum. We have HFCs from semiconductors, that's all our electronic goods. And then we have this sulfur hexafluoride, which is also in the production of magnesium and a lot of electronic uses. Okay, wow. So here's some things about our greenhouse gases. So the global warming potential compound, let me go over here for a second. Global warming potential is the influence a molecule has on climate change. And we use carbon dioxide to kind of compare the other chemicals. So if carbon dioxide can warm the climate by a factor of 1, look at the other ones. Methane can warm it by a factor of 28, so it's 28 times more powerful than a carbon dioxide molecule. Nitrous oxide, 265. All of these are in the CFC family. And look how long they stay around. Quite a while. So those CFCs are basically still up there from when we first started making them, and will be for a while. And then we've got good old sulfur hexafluoride that'll like basically never go away. So even though we don't use a lot of it, it's gonna be there all the time. So 2 graphs to look at. The global warming potential compound, so carbon dioxide, remember, is 1. Methane is 28. Nitrous oxide barely makes it on our graph, HFCs and sulfur hexafluorides, because we've got this huge scale, right? So just remember that. How long does it last in the atmosphere? So carbon dioxide is going to last a bit. Methane goes away pretty quickly, but it's powerful while it's there. And then nitrous oxide and HFCs are lasting pretty long, but these sulfur hexafluorides basically are forever. So clearly, sulfur hexafluoride has a huge global warming potential and it never goes away. So why are we using that stuff? So we need to talk about that a little bit too. Okay. Water is a big contributor to greenhouse gas emissions. So like we said earlier, warm temperatures evaporate the water and increase how much water goes into the atmosphere. But water also can form these clouds, which can decrease the heat by reflecting sunlight. But also down here, it's trapping heat because the heat's trying to escape, and then it bounces off the cloud and stays on the surface of the earth. So again, this is a negative feedback loop, and this is a positive feedback loop down here. So water kind of is a dual edge, but also We need water, it's the source of life. So in climate science, we kind of let that go unless there's something that humans are doing to cause this to happen more accelerated. So the other things we're doing that are heating the planet, causing the water to evaporate, is what we look at usually. All right. If we have more greenhouse gases, temperatures are going to rise. That's why they called it global warming for a long time. Describe what could happen for the following. So the sea level is going to rise. Think about, why will the sea level rise if we increase the temperature of our planet? And so your answer should be down here. Water molecules expand when the temperature is going warm. That's basic chemistry. So if the sea level rises, what are some consequences? We'll have loss of habitat, and that's for people and animals and plants, for all life. Don't just be human-centric there. What else could happen? We would lose habitat. We would have our food webs affected. We will have loss of land. It'll become underwater, which will affect the biome. The biomes will shift. There's lots of things that can happen. Now, another thing that can happen is the ice sheets can melt. Now, when we say ice sheets, this is a number one misconception. That's land ice. It's not the little ice caps that are floating on the ocean. We're talking land ice, because if it's warm, this is going to melt. It's going to run off and make its way to the ocean, and that will contribute to sea level rising. Think about the ocean. Here's an ice cap. It's already floating on top of the ocean, so it's not really doing much to like contribute to the sea level rise. It's actually cooling it, right? Because it's ice. Anyway, so we're talking about the land ice melting and contributing. That's supposed to be land, contributing to this freshwater addition to the existing ocean water already. Okay. Another thing that can happen if we get a warmer planet, we're going to increase our diseases, our disease vectors. Have you ever played that game where you're like try to like spread a disease through the whole world? I forgot what it's called. Vector maybe? But think of the planet at the tropics. It's really warm and it's moist, and that's where most of the diseases are. Tropical diseases. You've got yellow fever, anything that a mosquito can spread, that Zika, malaria, the list could go on and on and on. But if we start increasing our temperatures, we're going to have a wider band of tropical type conditions, and so mosquitoes will be able to thrive in places they previously couldn't, and they will spread these diseases through more parts of the planet, and that's going to increase our illnesses and affect our populations. Okay, so if the sea level rises, we're going to have less land, less resources for human populations and for plant and animal populations. If we have a disease vector problem, that's going to be an increase in our death rates, because more people are going to die from these diseases, and that's going to affect our populations as well. Okay, and remember, Malthus, one way to control human population is famine, disease, and war. We're kind of good at all three of those, aren't we? Okay, one more thing, this methane and ice. So there's this compound called a methyl clathrate. What? That's a crazy vocabulary word for you. And they could have something to do with increasing global temperatures now. So a clathrate is just a substance in where one molecule forms a little like trap over another molecule. And so ice is trapping methane in biomes like in the tundra, the permafrost. And so as molecules, or as bacteria are breaking down different things like dead plants, dead animals, when things decompose, they give off methane, and these methylclathrates trap the methane in an ice crystal. And so as long as the permafrost stays frozen, or as long as these ice cores areas stay frozen, it's not a problem. But what happens if it's global warming and the ice melts? Then they're going to release methane. And we know methane is a pretty good greenhouse gas. It was that 28 power one. And so if we all of these spots with methyl clathrates start to release or uncage the methane contained within them, that could alter our global temperatures and put some more methane in the atmosphere, and it could become a problem. So that's our lovely story of greenhouse gases and global warming. Please realize one more thing. I'm going to put a little caveat over here. Global warming is not the right term anymore because it is not warming everywhere. So you have places where temperatures will increase, but you will also have places where temperatures will decrease, and you will have places that were droughts now become flooded, and vice versa. And California kind of experienced that in 2023. We got so much snow. It was way more snow than we should have gotten. It was crazy, and it altered how our entire water system worked in California. It replenished enough to get us out of a drought. Whereas the East Coast didn't have any snow, and they didn't even have a ski season because it was hot and warm and 80 degrees. So usually where it's warm in one area, it's going to cool in another area. And where it's usually rainy in one area, it's going to become a drought, and it'll flip the other way around as well. So that's why we like to now use the term climate change. And even now we say climate disruption. That's a L. Okay, so just some things to keep in mind for your exam.